Hey guys, Professor Dustin here. This section of the class is called rotational dynamics, but before talking about that, I need to cover one more aspect of statics, and that is the fact that we can have these things called pivot forces. So recall that for statics we have the sum of the torques on an object is zero. That's the condition for rotational equilibrium. But equilibrium also means that the object is not moving at all. It has no linear acceleration as well. So that means that the sum of the forces is also going to be zero. And we'll see that we will need both of these equations in order to fully understand why an object stays in static equilibrium. So for an example here, I'm going to use this beam, which is like stuck against a wall or something, and there's a rope holding the beam right there, and we know what this angle is. This is going to be a massive beam, so it has a force due to gravity acting on it. So the first thing I want to do is I want to write down the torque due to both the force of gravity and of the rope. So what I've done is I've added forces to this picture. So I've put the force due to the tension, that's a blue arrow right there, and I've put the force due to gravity acting at the center of mass of the beam. The force of gravity always acts at the center of mass of extended objects. I've also said that, okay, the rope is acting at distance d from the end. As you recall, we did an example very much like this in class, and we found that the tension due to the rope is L minus D, so the position from the pivot point is L minus D, times the tension of the rope times sine of that angle theta. And so the trick is to make sure you understand why that angle right there is the angle in here. But we did that part in class. For gravity, the torque due to gravity is the distance that gravity acts from the pivot point, that's from here to there, times Fg. In that case, this is m times g. So now if I want to say, okay, I'm going to add up these torques, and I hope that they're going to be zero. So here's the torque due to the rope, L minus D t sine theta. Here's the torque due to gravity. I put a negative sign here. Basically, all that matters is there's a relative negative sign between the torque due to the rope and the torque due to gravity. I've also used the right-hand rule, taking outwards as positive, to find out that this guy is negative. So these things should add up to be zero, and for instance, if I knew the mass of the beam and the angle, maybe I could find the tension required on the rope. Okay, fine. That's by calculating the torque about the point of rotation right here. But now I also have the sum of all the forces on this beam has to be zero. That's a requirement so that this beam isn't accelerating up or down or left or right. So let's write down Newton's second law on this beam in the x and y directions. And let's see what happens when we think about the acceleration having to be zero in this case. So here I've written down the sum of the forces in the x and y direction. I started with the x direction using a coordinate system like there. I'm going to have the only thing that's acting in the x direction is the component of the tension in the x direction, so that's directed along the direction of the beam. So that's t cosine theta. I put a minus sign because I put the positive direction in the x direction outwards, so that direction is negative. In the y direction, I have two forces, the y component of the tension that is acting perpendicular to the beam, that's t sine theta, minus Fg, which is the force due to gravity. If I think this thing is in static equilibrium, I should set these things equal to be zero, right? But that's immediately a problem, because I have an equation here where it says negative t cosine theta is zero. Up here I could have solved for the tension, but this is apparently inconsistent with the idea of the tension not being zero. This says that either the tension is zero or cosine theta is zero, but neither of those things are true. So obviously something is missing in this equation. There are some extra forces on this beam that we're not taking into account of. And of course, we know that's true. We said originally that this beam is fixed to the wall. Well, the wall is doing something to the beam. In fact, the wall is holding the beam to the wall. So there's a force on this pivot point. Now I don't know anything about that force, so I'm just going to call it F and call it FF, Fx, and Fy in two different directions. So I've picked Fx to be towards the positive x direction and Fy to be towards the positive y direction. Those are totally arbitrary. I could have picked anything I wanted, but now that I have those on there, I can add them to my Newton's second law. So let me get rid of these zeros and say, okay, this direction I now have a plus Fx, which has to be zero, and in the y direction I have a plus Fy, which has to be zero. Okay, well that's great because now I have this equation, I can solve it and simply write that the force that the pivot has to act on the beam with is t cosine theta in the positive direction. I picked this to be positive direction, I got a positive sign. Of course that makes total sense, right? If the rope is pulling the beam this way, in this direction it's pulling it this way with t cosine theta, the pivot point must be counteracting it with t cosine theta, with the component which is pushing against the wall. This is Newton's third law, right? I can also solve this equation for Fy, and I get mg minus t sine theta. And that just says that whatever the wall is doing, if the tension is not balancing against gravity, that is, if the Ty isn't balanced exactly against gravity, then the wall has to act in the y direction to hold the beam up, or maybe even push the beam down if the tension is too large. So we don't know anything more about this equation until we actually solve for the tension up here, and it depends on the details of the problem. But the key is that we put the tension and gravity on here because we knew they were there, but we didn't know what the pivot was doing. We couldn't use the torque equation to find out what the pivot was doing. We would have to use Newton's second law. But of course, now this begs the question, if I wrote these down, should I have put those into the torque equation, right? I added more forces to the problem. I should have done that originally in the torque equation. Well, let's try to write down what the torque due to Fx and Fy would be. So there's the torque due to Fx and Fy, and I've just written these phi1 and phi2. I would have to figure out what those phi1 and phi2 are, but I should see something immediately. In the torque equation, I want to use the position of the force relative to the pivot point. This is the distance from the point of that it's pivoting at to the place the torque is being applied. Same with the gravitational force, it's from the pivot point to the center of mass, L/2. What's the distance from the pivot point to the point at which the pivot is acting? That's 0. It's acting at the pivot point. So these r's are 0, and both of these things go away. So that means that we're totally safe finding the forces acting at that point because they don't enter into the torque equation. Typically when you deal with these problems and you want to know what the forces at the pivot point are, that means you just have to pick the 0 point to be the pivot point. If you pick the 0 point to be the pivot point, then the torque due to the forces acting at the pivot point drop out and become 0. Okay, so thank you guys for watching. This has basically been a little bit of an augmentation of our statics problem. Instead of having just doing some of the torques being 0, we're going to have to start considering some of the forces being 0 and the forces acting at a pivot point like this. The only real complication there is we want to make sure that we always pick the location to calculate the torques about the pivot point, because that will make things easier. And we also have to remember that we may have additional forces in our Newton's second law that we don't consider without thinking about that the pivot is actually acting on the beam. Okay, thanks for watching, and I'll see you guys in class.